Here we look at the second way to reduce esters. Specifically, this is known as the DIBAL reduction because we're using the reagent diisobutyl aluminum hydride, commonly referred to as DIBAL. Now, DIBAL has the structure seen here. It's an aluminum with, as the name would indicate, a pair of isobutyl groups. And DIBAL allows us to do with esters some things that are a little bit different than what we can do with most of our other reducing agents. So, the most common way to reduce an ester is with LAH. But if we reduce an ester with LAH, we don't have any real control on that reaction. It's going to form the aldehyde. And then because an aldehyde is presumably more reactive than the ester, as soon as that aldehyde gets formed, that aldehyde gets reduced again to the alcohol. The advantage, though, with DIBAL is that with DIBAL, we, at least in theory, this is one of those reactions that always works well on paper, sometimes works well in the lab. But at least in theory, we have the option of whether we want both reductions to take place and form the alcohol, or if we just want the one reduction to take place and we want to stop at the aldehyde. So how does this occur? So as with many of these reduction mechanisms, our mechanism is going to be probably a bit of a simplification. In many reduction reactions, what's actually going on in solution can be a lot more complicated. We're just going to cover the basics that we need for this level of organic chemistry class. But as with any other reductant that you've learned about, such as LAH or sodium borohydride being the two most common, that hydrogen being attached to a metal, a very non-electronegative element, is actually going to have the majority of the charge there. And therefore, that hydrogen becomes a decent nucleophile. So the hydrogen adds here. We kick the electrons up onto oxygen. As a result, we form the following. We form this aluminum complex to what was the ester. Our hydrogen that we added is not drawn in, but we can go ahead and do that. Well, here's the point where you've got your control. It all depends upon the temperature that you run this reaction at. If you run this reaction at minus 78 degrees Celsius, that's the temperature we achieve with a dry ice bath. But if you run this reaction at minus 78, this complex with the aluminum, coordinated to the oxygens, can be stable, and in a lot of cases is quite stable. The reason that something like LAH just immediately goes to the alcohol is the intermediate that forms is not stable. It immediately goes to the aldehyde, and the aldehyde continues to react. Well, if you do your LAH reduction at room temperature or warmer temperatures, the same thing will happen. You'll immediately form the aldehyde, and the aldehyde will get reduced. But If you run this reaction cold at minus 78, this aluminum complex is relatively stable. And then while at minus 78, you can quench the reaction. So we quench the reaction, that'll allow, and warm it up. That'll allow our aluminum complex to break down. But by the time it does, and it forms the aldehyde, by quenching the reaction, we don't have any of our reductant present, and so the reaction can't go any further. So this way we have some options, and when we have an ester that we want to reduce, it can go in either direction. Again, if we run it with LAH or we run it with DIBAL at warmer temperatures, our ester will get reduced all the way to the aldehyde. But if we do it at cold temperatures and then very carefully quench the reaction while it's still cold, in many cases we can get the ester to be converted specifically to the aldehyde, which is going to be of benefit to us in synthesis, because then we have any of the numerous reactions of aldehydes that we've learned.